In this lecture, we are going to discuss the structure of finite fields. We begin with a definition. The characteristic of a field F is the smallest natural number n such that 1 plus 1 plus 1 n times is equal to 0. If such n does not exist, we say that characteristic of a field is equal to 0. For example, the field of rational numbers has characteristic 0. On the other hand, if our field F is finite, then such a number will exist. So we say that F has a finite characteristic. And if F has a finite characteristic, it's easy to see that the characteristic of F must be a prime number. Indeed, let us show that characteristic of a field cannot be equal to 6. In such a field, 2 will be non-zero, and 2 is 1 plus 1. And 3 will be non-zero, which is 1 plus 1 plus 1. And if we multiply 2 with 3, we will get 6, which is equal to 0 in the field of characteristic 6. This would mean that we have divisors of 0, and we know that in a field we cannot have divisors of zeros. This is why the characteristic of a field cannot be a composite number. For today's lecture, we fix P to be the characteristic of F, and so this is prime. If we consider a subfield in F generated by 1, then we see that this subfield is isomorphic to ZP. This tells us that any finite field contains ZP as a subfield. Then we can view F as a vector space over ZP. This is a special case of a general situation. So if we have a field with a subfield, then the larger field may be viewed as a vector space over a smaller field. And since our field is finite, then the dimension of F as a vector space over ZP is a finite number. But we can easily count the number of elements in an n-dimensional vector space over ZP. And from here, we conclude that the number of elements in F is a power of P. It's P to the power n, where n is the dimension of F over ZP. So this tells us that size of finite fields could only be powers of primes. And in fact, for each prime P and for each n, there exists essentially a unique finite field of this size. Let us construct a finite field with P to the power n elements. Let F be an irreducible polynomial of degree n in the ring of polynomials with coefficients in ZP. And we set F to be ZP of x quotient by ideal generated by polynomial f. So we have the following basis of f as a vector space over ZP. So it will be 1, x, x squared all the way up to x to the n minus 1. So from here we see that dimension of f over zp is equal to n, and hence the size of this field is p to the power n. And since f is irreducible, this construction gives us a field. This construction may give an impression that we can construct different finite fields of the same size by taking different irreducible polynomials of the same degree. However, we're going to see that all these fields are in fact isomorphic. Let us look at the multiplicative group of our field. So this group is denoted f star, and we need to remove the zero element to get a group. So this tells us that the size of the multiplicative group is p to the power n minus 1. We have the following important theorem. The multiplicative group f star of a finite field is cyclic. Let's give the sketch of a proof. We know that this multiplicative group is a finite abelian group. And this tells us that this group is isomorphic to a direct sum of cyclic groups. By the fundamental theorem about the structure of finite abelian groups. And these primary cyclic components will have orders that are powers of primes. Let us look at an example. Let's consider a field of characteristic 7 with 49 elements. Then the size of its multiplicative group is 48, which is 3 times 2 to the power 4. Let us give a list of all abelian groups of order 48. So these are Z2 plus Z2 plus Z2 plus Z2 plus Z3, then Z2 plus Z2 plus Z4 plus Z3. We have Z4 plus Z4 plus Z3. We have Z2 plus Z8 plus Z3. And we have Z16 plus Z3. Up to an isomorphism, there are 5 distinct abelian groups of order 48. Which of these groups is cyclic? Well, it's the last one. So the last group is isomorphic to Z48. If we take an element which has 1 in the first component and 1 in the second component, then the order of this element will be 48. Let us show that the multiplicative group of this field must be the last group which is cyclic. By Lagrange's theorem, we have that for every alpha in f star, alpha to the p to the n minus 1 is equal to 1. Let us introduce the notion of exponent. The exponent of a group G is the smallest natural number m such that for every a in the group, a to the power m is equal to identity. By Lagrange's theorem, we see that the exponent of a group is a divisor of the order of the group. Let us compute exponents for these abelian groups. So the first group has an exponent of 6. If we take any element in this group and take its 6 multiple, then we'll see that we'll get 0 in each component. And it's clear that 6 becomes the exponent of this group. For the second group, the exponent is 12. This is the least common multiple of 4 and 3. So it is also 12 for the next group. Then here it's 24. And for the cyclic group, the exponent is 48. We make the following claim, that the exponent of the multiplicative group of a finite field is equal to its order. Indeed, let m be the exponent of f star, then this tells us that for all alpha in f star, alpha to the power m is equal to 1. Consider the following polynomial, x to the power m minus 1, and view it as a polynomial in zp of x. We see that the number of roots of this polynomial in f star is equal to the order of this multiplicative group, because every element of the multiplicative group is a root of this polynomial. But we have that the number of roots of a polynomial cannot exceed the degree of a polynomial. From here, we obtain that the size of the multiplicative group cannot exceed m. But Lagrange's theorem gives us the opposite inequality. Lagrange's theorem says that the exponent cannot exceed the order of the group. So this tells us that the exponent of the multiplicative group of f star is equal to the order of this multiplicative group. And then we make the following observation. If the exponent of a finite abelian group G is equal to its order, then G is cyclic. In this example, we see that among abelian groups of order 48, the only group whose exponent is equal to the order, which is 48, is the last group, which is cyclic. And the claim of this observation can be easily derived from this classification theorem about the structure of finite abelian groups. Combining these two observations together, that the exponent of a multiplicative group of a finite field is equal to its order, and this observation about exponents of finite abelian groups, we obtain the required claim that the multiplicative group of a finite field is cyclic. As a corollary, we get that a finite field may be generated by a single element. So this means that f can be viewed as zp of alpha for some alpha in the field. And the proof of it is we take alpha to be a generator of the multiplicative group of the field. then Zp of alpha will contain all powers of alpha, and thus will be equal to f. For such an element alpha, consider its minimal polynomial. Then we know that Zp of alpha is isomorphic to Zp of x, quotient by ideal generated by this polynomial f. From here, we conclude that every finite field may be constructed as this quotient, Zp of x, quotient by ideal generated by an irreducible element. So our construction that we gave before is a universal construction of finite fields. Every finite field may be constructed in this way. And this guarantees that the degree of this polynomial will be equal to n, which is the dimension of f over Zp. The converse of this does not hold. If we know that the minimal polynomial of alpha is equal to n, this does not mean that alpha is a generator of the multiplicative group. From Lagrange's theorem, we know that for all alpha in multiplicative group of the field, alpha to the p to the n minus 1 is equal to 1. If we want something like this hold for all elements of f, including alpha equals 0, then all we have to do is we need to multiply by alpha both sides. Then we conclude that for all alpha in f, alpha to the p to the n is equal to alpha. So this tells us that alpha is a root of the polynomial x to the power p to the n minus x. And then we get the following remarkable formula, that x to the p to the n minus x is written as a product over alpha in f of x minus alpha. So here we have a polynomial of degree p to the power n, and we found p to the power n roots of this polynomial in the field f. This means that the following factorization holds over the field f. As a corollary, we get that a finite field with p to the power n elements is a splitting field of a polynomial x to the p to the n minus x over Zp. So this means that we take the extension of Zp where we add all the roots of this polynomial. And the consequence of this is that a finite field with p to the power n elements is unique up to isomorphism. This follows from what we proved earlier, that the splitting field is uniquely defined up to an isomorphism by its polynomial. Consider our previous construction of f as Zp of alpha, where little f is the minimal polynomial of alpha. Then we see that polynomials f of x and x to the p to the n minus x have a common root alpha. This tells us that the GCD of x to the p to the n minus x and f of x is not equal to 1. And since f is irreducible in Zp of x, this tells us that the polynomial xp to the n minus x is divisible by f. But as f, we can choose any irreducible polynomial of degree n. So we conclude that the polynomial x to the p to the n minus x is divisible by every irreducible polynomial of degree n in the ring Zp of x. Another corollary that we get here is that a finite field with p to the power n elements is a normal and separable extension of Zp. The claim that this extension is normal follows from the fact that this is a splitting field extension. So it's a splitting field of the polynomial x to the power p to the power n minus x, and every splitting field extension is normal. To show that it's separable, we need to show that an irreducible polynomial of degree n does not have multiple roots, but this irreducible polynomial is a divisor of x to the p to the n minus x. And we see that x to the p to the n minus x has no multiple roots. Thus, f has no multiple roots either. Let us discuss subfields in a field with p to the power n elements. Clearly, every subfield must be itself finite, and thus it must have p to the power k elements for some k. We state the following theorem. A field f with p to the power n elements has a subfield with p to the power k elements if and only if k is a divisor of n. So if we consider an example of a finite field with p to the power 12 elements, then inside we have a finite field with p to the power 6 elements and a finite field with p to the power 4 elements. And the subfield with p to the power 4 elements is not a subfield in fp to the power 6 because 4 is not a divisor of 6. Then inside these fields we have fp cubed and fp squared. And fp squared is contained in both fp to the power 4 and fp to the power 6. And finally, at the bottom, we have the primary subfield Zp. This is the structure of subfields in a field with p to the power 12 elements. Let us prove this theorem. Let big K be a subfield in F with p to the little k elements. Let S be the dimension of the big field over the subfield K. Then, by counting the number of elements in the S-dimensional vector space over the subfield K, we get that the number of elements in F is equal to number of elements in K to the power S. This tells us that p to the power n is equal to p to the power k to the power s, and this tells us that n is equal to k times s. So k is a divisor of n. To prove the converse, suppose k is a divisor of n. Then I give you as an exercise to show that x to the p to the n minus x, in this case, is divisible by x to the p to the k minus x. This proof is based on the following formula, that a to the power m minus 1 is equal to a minus 1 times a to the m minus 1 plus a to the m minus 2 plus a plus 1. And in this proof, you use this formula twice. First, you use it to show that p to the power n minus 1 is divisible by p to the power k minus 1 as integers. And then you show that x to the p to the n minus 1 is divisible by x to the p to the k minus 1 minus 1. As a corollary, we get that if little k is a divisor of n, then a field f with p to the power n elements has a unique subfield k with p to the power k elements. This follows from the fact that k can be described as the set of elements beta in F, such that beta to the p to the power k minus beta is equal to 0. In other words, k is a splitting field of x to the power p to the k minus x, which is a factor in x to the p to the n minus x. Next, let us define the Frobenius map. This is a map phi from f p to the power n to f p to the power n, which is defined by phi of alpha is alpha to the power of p. Let us study the properties of the Frobenius map. First, we claim that phi of alpha times beta is equal to phi of alpha times phi of beta. And likewise, phi of alpha plus beta is equal to phi of alpha plus phi of beta. The first property is obvious because alpha times beta to the power of p is equal to alpha to the power of p times beta to the power of p. The second property uses the fact that we are in characteristic p. So if we write alpha plus beta to the power of p, then by binomial theorem, this is the sum k goes from 0 to p choose k, alpha to the power of k times beta to the p minus k. But if k is different from 0 and p, then this binomial coefficient p choose k is divisible by p. And thus, in this binomial expansion, only the first and the last terms will survive. We get alpha to the power of p plus beta to the power of p. The third property is that for every a in Zp, phi of a is equal to a. If we apply the Frobenius map to the elements of the subfield Zp inside F, then the Frobenius map will fix them. This is the little Fermat's theorem. Is that for every a in Zp, a to the power of p is equal to a. And the fourth property of the Frobenius map is that if we apply it n times, then we get identity. So here, if we apply the Frobenius map n times to an element alpha, then we're going to get alpha to the p to the power n, and we know that this is equal to alpha for all alpha in F. As a corollary, we conclude that the Frobenius map is an automorphism of f to the p to the power n over zp. This is an automorphism of this field that fixes elements of the subfield zp. Since fp to the n is an algebraic extension of zp, we can view fp to the n as a subfield in the algebraic closure zp bar of zp. Consider all possible field embeddings. Maps of fp to the n into this algebraic closure. Since fp to the n is a normal extension of zp, we conclude that for every such theta of fp to the power n is fp to the power n. Since every such embedding theta must preserve the set of roots of the polynomial x to the power p to the n minus x. So we get that theta is also an automorphism of f to the p to the n over zp. But we also saw that fp to the n is separable over zp. So this tells us that the number of such embeddings theta of fp to the n into zp bar is equal to the degree of the extension fp to the n over zp, and this is equal to n. And as a corollary, we conclude that the powers of the Frobenius map identity phi squared up to phi to the n minus 1 exhaust all automorphisms of fp to the n over zp. And this tells us that this group of automorphisms of fp to the power n is a cyclic group of order n generated by the Frobenius automorphism.